SwayamPrabha. Digital India. Educated India.
Shown here is a typical schematic of how a mixing layer would look like. Let us say we have fuel and oxidizer here, and there is a splitter plate there in between, and there is a, you have Kelvin-Helmholtz instabilities, that is this shear layer will tend to roll up and gets organized and roll up, and the flame front also will go with this shear layer, and it will so this oxidizer will get entwined into this vortex and then roll up and get mixed and burned. So so that's like an idealized situation, but in reality you will have these things happening within walls in a dumb combustor, let us say, and so you have unburned mixture of reactants. Let us say we have a premixed flame and you have hot radicals in this recirculation zone, and so the vortex tries to roll up and you have the unburned mixture get entwined into the vortex this way, and you have hot products here which are entwined, and there is an interface here where strain rates would be high and there will be a lot of turbulence. So once you, so the large scale roll up does not necessarily ensure mixing, but then once you really have molecular mixing and then everything is well mixed, then you have sudden ignition and you have combustion, and that is what we are looking at. And from the basic fluid mechanics of jets, we saw that there is some kind of instability waves, and they scale as so if your the frequency is Fi, I denotes initial region, so they scale with a straw hole number based on the momentum thickness at the exit and the velocity at the exit, and of course there will be vortex merger and interaction and so on, and eventually you will have a lower frequency and a bigger vortex and which is scaling like STJ, that is the at the jet exit or at the end of jet core you have a straw hole number scaling of in terms of the diameter of the jet and the jet exit velocity, and this frequency would be usually lower and its straw hole number is of the order of 0.25 to 0.5. So this frequency would be called preferred frequency of the jet. So if you excite at these frequencies, then you will get very large response of the jet, and this vortex will become much more coherent and the spectra will become more sharp. So this is where we stop, and are there any questions? So development of large scale structures is beneficial for the enhancement of large scale mixing or bulk mixing in the shear layer, but this does not necessarily mean that there will be molecular mixing, because you need small scale mixing. So in the presence of large scale structures, transition to fine scale mixing is initiated by the braids of vortices where there are high strain rates or high velocity gradients, and that is where the in between the high speed stream and the low speed stream, and of course initially the turbulence production is restricted only there, but then when the vortex rolls up, this will increase, and also the presence of walls will also increase this fine scale mixing and turbulence, and that leads the fuel air mixture to get entrained into the vortex and then burn suddenly. So you are not having a continuous burning in this kind of situation, but you have this mixture that is going to burn gets entrained into the vortex and then comes in, and when they are mixed in a molecular level, bang, it burns. Okay, is this concept here. So if you are talking about a diffusion flame, you have fuel and air mixing from either sides, but if you are having a pre-mixed flame, you may have reactants on one side and hot products on one side, but the hot products which has the hot radicals, they have to mix well with the cold reactants, only then the burning will happen.
This is a premixed flame, right?
In either case this scenario would be working. So if it is a diffusion flame, you will probably inject somewhere here, many times you inject at this step or slightly behind the step, and if it is a premixed flame, fuel and air are coming together, but you have hot radicals here. In either case some scenario like this would be valid.
So for controlling this, do we ever use like multiple injections are there. By changing the angle of injection, can we change the?
Yeah, I think that's possible, because by changing the angle of injection, you would actually be changing the mixing time and the residence time and the convective time scale and all that. So in effect, you are affecting the time delay. So yes, it is possible. Another possibility is you can change the what is being injected, the distribution injection, and then if you are talking about a annular combustor, you can have each injector have a differently having a different injection velocity, so that you have a time delay, but each injector has a different time delay. So if it's like a distributed time delay, everything is not coming bang at one shot, but instead one comes first, another comes next, another comes next. So the if everything acts together, there is coherence, and then you have a very large heat release at one instant. Instead this tends to get distributed, so that will reduce the possibility of instability happening. That's a very good point. Any other questions?
Can we use this in a annular combustor? Because if the passage or the inlet diameter is small, then we can use this, but if the inlet diameter is large,
yeah, in annular combustors what they typically do is they would have different burners located along the annulus. So there will be a number of burners. You can have can burners, or you can have just annular thing with swirlers. So you can have several swirl burners, and not necessarily backward facing step, but often with swirl. They may have a step also, but there will be a swirler to have rapid mixing and so on, and that's possible. I mean, can is of course there, but the aircraft engines, they are annular. So the strategies could work. Anything else? So we also looked at several different configuration of dumb combustors, and with bluff body, without bluff body, with V gutter, with cylinder stabilized flames, and so on, and we saw that all of them kind of fits into this kind of category, where there is possibility of a big vortex or a large scale coherent structures coming in. Now so the development of large scale coherent structures depends on the relationship between the acoustic velocity and the flow instability frequency. So the if the acoustic frequency is very far away from the flow instability frequency, then there would be hardly any interaction. But if you are exciting at the preferred mode frequency, that is the frequency that is here, I think there is a good chance that you can make the jet very coherent, and you can have very large amplitude fluctuations. But if you are having a cold flow, that is there is no combustion, the vortex itself, you will produce some sound, but it is not that much to create a feedback. But in the presence of combustion, the mixture rolls up in this vortex, and then you burn, and that gives the unsteady heat release which connects the feedback, and then this plays a very big role in creating sustaining this instabilities. Of course there are vortex related instability, like for example flute or something, where you are actually having vortices, and that is actually producing sound, and you are locking onto this frequency of the pipe and so on, which is the resonator in the flute. If there is time, we can look at that later. So the combustion is initiated at the circumference of the large scale structures, where secondary streamwise scale eddies are growing, initiating the process of transition to fully turbulent flow. So you have this, and the vortices are being convected down, and the combustion happens somewhere down, and the vortex is being convected down, and the molecular mixing is taking place. So just as when the molecular mixing has happened adequately, it burns, and by then this mixture would have been brought down some distance. So that decides the location of the heat release.
What do you mean by circumference?
Like here in this region. I mean, yeah, it's vague term, yeah. So the acoustics kind of reinforces the shear layer and the structures in the shear layer, and the combustion is related to these flow structures. That's what that's all I am saying. So it's not like we are often tempted to think that particularly because of the pictures drawn in undergraduate textbooks, we would tend to think that there is a flame like this, and when you have a jet, you tend to think that jet has a core and there is a entrainment region and there is a core and a mixing region. I mean these are I mean yes, in an average sense this may be true, but in reality I mean it's very far from this, like this or this is more like the reality, and this is how the flame happens, and it's never ever that you will have a nice flame standing like a V. I mean yes, it is possible in a simple Bunsen burner flame or something like that, but not in a real combustor. You would have vortex shading if it is coming at any serious velocity, and you would have a vortex roll up and the combustion would be periodic, and if you have a jet, I mean jet will have vortices, and it's this is the, if you time average over a large time you would get this picture, but instantaneous picture is highly unsteady. So we have to worry about this, particularly in combustion, where once you have periodic heat release rate, it is going to modulate the combustor, and any combustor which has been built of this sort has had instability under some condition or the other.
This is very much necessary, this instability, this pulsating behavior.
See, yes, can you rephrase the question? Pulse combustor doesn't necessarily mean pulsating behavior, so I don't know what you, can you restate your question? I am not quite understanding.
Pulse jet engine, in pulse jet engines, such repeating cycles of vortices and.
Okay, oh, you are asking whether hydrodynamic instability or coherent structures are a necessary condition for pulsating instability. No, it is not necessary at all. We showed example and I showed movies of a Reiki tube and also a Bunsen burner flame with a pipe around it. I didn't quite see any serious, I mean you saw wrinkles but not really any vortex related roll up and so on, although you can set up those experiments to have them also, but there it was not really a necessary, we still had instability. But this is another mechanism which comes into play not in those simple laboratory combustors, but more like in practical combustors, where you have to have a serious flame holder, like in afterburner where you have a V gutter or you have this bluff body stabilized flame, or which like in industrial burners and so on. So this is one type of mechanism. So it is this is a serious mechanism which can drive combustion instability, but this is not the only mechanism that drives instability, but this is a pretty serious mechanism which is there in practical combustors. Okay, did that answer your question? No. Ask.
This instability has to be a necessary condition for pulse jet engines.
The pulse jet engine is a kind of pulse combustor.
So if there is no instability, it will work right.
No, it thrives on instability because it is self aspirating. So you have, it is like that in the laboratory we showed a jelly jar combustor where you have a fuel air mixture, it burned, then it again entrained air, it then mixed and then burned. So similarly pulse jet engine, it entrains, it brings in air, when the pressure in the combustor is low it just takes air, then it burns, sends the thing out, and in that process generates the thrust, then pressure comes down, it valve opens, takes in air. So it will not work, it has no compressor, right, so it won't work without the pulsating. And in fact for people who are trying to make very small engines, micro engines or whatever, they think of this kind of pulse jet as a possible option, because to make a compressor at that stage would be quite difficult at that small size.
So basically it's not the vortexes that are formed inside that is holding the flame in a pulsating. Actually this is holding.
No, flame is being held by the recirculation zone. So we have to have a low velocity zone to have the recirculation zone. So that is the purpose. So we are not having the recirculation zone, or we don't need a vortex to hold the flame, but we need a low velocity zone. But we also we are greedy, we want to pump in a lot of mass flow rate, So we want to have a high velocity stream coming in. So moment there is a low velocity stream and high velocity stream, there will be kind of the mixing layer or the shear layer between them will be unstable and have this Kelvin-Helmholtz instability and roll up and so on. So we are not having the bluff body to shed vortices, we are having it there to hold the flame, to have a low velocity region where there are radicals that are available which will ignite the coming mixture and so on. But you can't have this and not have that. If you want this low velocity zone, then naturally there will be an interface between high velocity and low velocity zone, which is the shear layer, and it will roll up, it won't stay nice and flat like this, that is only in undergraduate textbooks. It will roll up and then it will cause this vortex shedding, and vortices being shed, that is by definition unsteady phenomena, and then that can carry the pocket of fuel air mixture and burn in a periodic manner. So I hope it is clear. I think now I understand the question. Yeah, okay. Anything else? Okay. So in summary, as what you said, due to fluid dynamic and combustion interaction, the heat release is periodic and pockets of high temperature flow are convected downstream from the burner exit. And people have measured this, I mean they have in the experiments with planar laser induced fluorescence experiments, with that is a laser diagnostic experiment. So you can illuminate the region with some kind of laser like UV laser which is tuned to OH radical and look at the emitted signal from the fluorescence, and you can do this with high speed imaging. There are cameras which can image things at several thousand hertz or even 10,000 hertz and so on. And even before this CCD cameras came, people are doing high speed film cameras and have done this in the 80s, and you can also see chemiluminescence, although chemiluminescence has a line of sight integration as opposed to planar laser induced fluorescence, which is a technique on a plane, but still you can see all of this with chemiluminescence and high speed imaging, and people have done that. So so there is a large scale structure and it breaks down into fine scale mixing, and so you have also this interaction between vortices, and walls and all that, which is quite complex, and I can't write a one dimensional model for these things understandably because you have to solve some 3D turbulent flow equations, but I am just saying the qualitative features, that is the best I can do. And I urge you to read some of the references, I urge you to read the 2 references that I have given and then the 215 references listed in each of them, that would be a good idea. So the high strain rates and the concomitant small scale turbulence generated by the merging or process of vortices creates intense turbulence, and it will accelerate the combustion. So the process may reinforce the periodic heat release of a forced reacting shear layer, in the sense you are rolling up and burning, but that burning does not happen as it rolls up, but then as it rolls up at some time everything would have completely mixed because of this fine scale turbulence, and bang, it burns at that time. So it is really a sharp intense heat release as opposed to a slow and steady burning, and if you do have a continuous kind of burning, then you do not have problem of instability. So another cause of sudden heat release rate which is seen in dumb combustor is sometimes the dumb combustors have low step heights, and the step heights depend on various performance considerations as to about the steady state performance consideration. But if you have low step height, what happens is the developing vortex downstream of the combustor can get impinged against the lower combustion wall, and there can be some kind of flapping mode. So the Kelvin-Helmholtz instability can combine with a sort of flapping mode instability. Try to draw a picture. So you can have either a premixed or a diffusion flame, in either way it is coming this way. And so you do have a Kelvin-Helmholtz instability. In fluid mechanics people often call it KH instability, and then you can also have this flapping shear layer. and that's another kind of instability, and both so it can start off with the KH instability, but then you have the step instability.
This is for low steps.
Yeah, when this step size is low. If it is very big, then this won't happen. You just roll up without interacting with the vortices. So if this, if I have
This is one the shear layer that is separated from the boundary layer is directly hitting without any roll up.
No, it is rolling up. I mean, it is unstable, but it didn't roll into a big thing, but instead it came down. And so if you have a very big wall, then there's a possibility that I mean it just rolls up. I mean, so you have this without interacting with the wall, but if this at some small enough step height, of course this can actually go and impinge on the wall. That's a distinct possibility, and there can be interaction between the Kelvin-Helmholtz instability and the step mode or flapping mode instability, which is very complex. And so so you have the developing vortex go downstream of the dump and impinge against the wall, and so again impinge is a very crude term. It's like one shear layer interacting with, when it comes close to the wall there is a boundary layer there and it's interacting with that. So it's not like something impinge doesn't mean it just goes and bang hits. So since the downward velocity of the vortex is large, a vigorous mixing occurs between the remaining unburned reactions and the combustion product, again leading to a sudden heat release as the flame as this mixture approaches the wall, and the energy is supplied to the acoustic field because the heat release oscillations are if it is in phase with pressure oscillations, and if it is out of phase it won't be adding energy. And sometimes this may be that some part of the flame may be adding heat in phase, some other part may be adding heat out of phase, but then what matters is what is the net energy addition to the acoustic field. Some part may add, some part may take out, so the net energy addition is what decides whether you are going to have acoustic driving and instability or not, and whether this amount of driving, the net driving that is there, is actually more than the losses or less than the losses. There is one more possibility. You can have combustors which are long and short, that depends on the purpose of the combustor. If you are trying to have a very long combustor and you want to take out the heat slowly and all that, then you may have long, but there is also a possibility where you may have short combustors where you do not have provision for a long combustor, like in aerospace combustors they are short.
Depends on the flow velocity, right?
Depend,
Afterburners are very long.
yeah, so depending on the flow velocity, the purpose of the combustion, and depends whether it's an aircraft combustor or a ground based combustor and why you are burning and so on. So if you have relatively short length, then the vortex will interact with the exit nozzle. The combustor is long, by the time vortex reaches the exit nozzle, dispersion would have set in and the vortex would have smeared out and would have lost some of its coherence and it would have spread out. But if the nozzle is close to the inlet, that is the combustor is short, then the vortex will come, it will still maintain its nice coherence and come and impinge on the nozzle. So at that time the strong mixing between cold reactants and the hot products will occur after the vortices impinge on the exhaust nozzle, creating small scale vortices, and this would be followed again by intense heat release in a short time, and if it is in the right phase it can add instability.
Does high temperature kill vortices? Or is vortices independent of temperature gradients?
See, when you have high temperature there are a lot of other phenomena that come in, and I can't give a simple straight answer to this. One is there is expansion of the gas across the flame, and the vortice and the flame, they are in some sense coming together but not exactly, and then there is also a further vorticity produced because the pressure gradient may not be aligned with the density gradient, so that is called baroclinic vorticity. So if they are not aligned, there is extra vorticity being produced. So very simple picture which I drew first is may not necessarily hold. There are the other factors, and which is dominant depend on the specific circumstances. So it is not like vortices cannot exist in high temperature region, and it will exist, and then the calculation gets more complex.
Plus since the combustion mainly happens at the shear layer boundaries, there can be situations when the boundaries split again, and
yeah,
during combustion.
Yes, so yeah, it's then it's if it is completely combustion, it may break down into fine scale turbulence and small vortices also, it's possible. So several scenarios are possible, and like I told you, I mean they are in that other paper by the one by Renard et al. With 215 references, they have given lots and lots of possibilities and experimental studies and numerical calculation explaining all this. So I mean it's a very complex topic, and I can't give a simple one-dimensional model about this.
And the vortices, when you interact with nozzle, it will be carried to the backstream, like after the combustion.
You mean out of the nozzle?
Out of the nozzle.
Yeah, so it can, so it depends on the amount of dispersion and what happens when it impinges. So it's one possibility is when it impinges, this mixing can happen, heat can be released, but then you can have this hot spots, they can travel through the nozzle if they are not dispersed. So if there is a, so these vortices are not coming in isolation, they are coming in a highly complicated flow. So it may be possible that, so high temperature pockets, called fancy name would be entropy spot, they are coming, and it can be dispersed or it can still stay as it is, it depends on the velocity profile, I guess you can imagine that. So if this thing is going to go through the nozzle, then what happens is as the hot spot goes through a acceleration, it is possible that it can generate acoustic waves, because there is a, you are having a entropy mode generate acoustic mode because of a non-uniform base flow. So in entropy mode and acoustic modes and vorticity modes, they are independent only when the base flow is uniform, but when the base flow is non-uniform, it's a possible, there is a distinct possibility that one mode may create another. So this is called entropy mode of sound generation. So when a hot spot, which, and why hot spots, because the mixing happens not continuously but with this roll up. So if this hot spot comes to the nozzle, and then there is a sound wave coming back, and then that can again give rise to thermoacoustic instability. So if it does not go through, then this mechanism does not exist. So the way they want to avoid this is to increase the somehow increase the dispersion of the vortex, that is it does not stay as a compact thing, and try to get rid of that. It's a very beautiful point that you are asking actually.
Hotspot is always related to vorticity in some way?
Not necessarily, it can be bad mixing also, but this I mean this is a fluctuating heat release, let us say in some sense, but it need not be. If you have bad mixing, you can definitely have that, and that can also go through the nozzle and create acoustic waves. But your specific question was, if it comes to the nozzle, will it go through, and if it goes through, what happens? That is what I am answering.
The instability is basically from transition from laminar to turbulent. Only when the shear layers completely transit to turbulent.
Can you repeat? You are asking a very deep question, so I have to pay attention.
So the Kelvin-Helmholtz instability, it's basically during the transition from laminar to turbulent.
No, you can have Kelvin-Helmholtz instability for laminar shear layers also. Shear layer will be unstable and roll up. It will in practical combustor, but you can have it not break down also, still be Kelvin-Helmholtz instability.
When you have a Kelvin-Helmholtz instability,
Yeah.
Why would there be small scales, like small scale mixing? Turbulence, only turbulence gives a small scale mixing.
Yeah, so it is in a turbulent flow. Turbulence has all the scales. So there is a possibility that when you have a turbulent shear like this, you tend to make small scale mixing, because in this region strain rates will be very high, and so you have small scale mixing, and the chance of the large vortices breaking down to small vortices extra, that can happen. If you have high velocity gradients, or if you have high strain rates, you can have small scales.
So essentially those vortices have to break down.
Yeah.
So when once they break down, why is this periodicity maintained?
But it comes periodically, then break down. So it's periodic to begin with. Start with the large coherent structure, and then it breaks down. So you can't get rid of that. You start with the shear layer here, and there are vortices and they are merging and all that, and there is only bulk mixing there, and because it takes some time for the small scale mixing, as you said, it breaks down after some time. So you can't break this big structure to begin with.
Only when it breaks down and we have smaller structures do we have a flame there. In the
Ignition.
larger structure we don't have sufficient mixing, so there is no flame in the larger structure.
There is no combustion in it.
Yes. So only after it broke down and after we have small scale turbulence,
Yeah.
we have combustion.
Yeah.
So if that is sufficiently far from this instability, then it should not be periodic.
Because the whole thing is starting with periodic, it is not starting with the whole thing. If you don't have the big scale and if you have small scale turbulence right from the beginning, then you will have continuous combustion, but it does not come right from the beginning. The fine scale turbulence is happening as the vortexes roll up. So initially this is not a steady picture, it just comes like this, then rolls up. So until it starts rolling up, the fine scale turbulence will be minimal. That is what I understand. So my knowledge on this subject is kind of second hand in terms of reading papers. I have never done experiments myself on this, so I am not an authority on this, but this is what I understand. But I understand that still there is lots to be done, and it is a very intensely debated research topic. Very nice. You are driving at a very important point actually. Anything else? So we will look at combustors with flame holders like ramjets, and I think a lot of people here are specifically interested in that. So this is an example given in this paper by Goodmark and Shadow. So you have combustors with flame holders where there will be a multiple shear layer interaction is a likely source of fine scale mixing, enhancements and sudden heat release. So during one cycle of pressure oscillations you will have two vortices of opposite sign shed symmetrically from both top and bottom surface of the flame holder, and as these vortices convect down they distort the flame surface and cause flapping of the flame branches. So this distortion will result in oscillatory increase in the flame surface area and hence results in an oscillatory heat release rate. So this surface itself will start flapping and oscillating, and you can have an increase and decrease in area. So the flapping of the flame branches may also cause periodic interaction of the flame front with the side wall, contributing to periodic heat release rate. So you will have in any case some kind of unsteady heat release rate, but in such combustors the flame will be somewhat long, and there is a possibility that the entire flame may not have the same driving or damping characteristics. Some parts may drive and some parts may damp. So whether oscillations are excited or not depends on I mean whether the net driving is more than net damping or not. So I mean and everything goes by what Rayleigh said. If the heat release is in phase with the pressure oscillations, you have acoustic driving. If they are out of phase, then you have acoustic damping. So you can also have very high strain rates causing flame extinction, that is another possibility, and we also have this baroclinic vorticity production because of the misalignment between the pressure gradient and the density gradients that occur during the roll up of the flame. So these things complicate the analysis quite a bit. Now I want to talk about another instability, another example where vortex shading can cause some kind of instability, like aerodynamic instability, but happens in combustors, in solid rocket motors.
Is it an external agent that is creating an acoustic field, or is it the combustion itself that creates the field?
In these cases, the acoustic itself is not strong enough to create a feedback, but you will have sound. If you put a microphone, you will measure, but it will not be strong enough to create a feedback. But in these examples, so the vortices just modulate the flame, and that causes the periodicity. Okay, so let me back the I will change the topic and I will speak about something else. So if you have like something like a whistle, it is like called headstone or something like that. So if you are actually producing a coherent structure of vortex, and that is coming from somewhere, and then it is interacting with another surface, and then forming a feedback loop, or like a whistle which the referees blow. So you have vortex shading, but there is some kind of feedback with a resonator. So if you have, okay, maybe I could speak about that rockets itself. Yeah, I will speak about the rockets, then talk about aerodynamic instability, and then try to tie up this with that. Okay, I think that is the best strategy. So your answer will have to wait a little bit when I speak about aerodynamic generation of sound, and I do not know if this bottle, the water height is right to generate the sound, but let us try. So here there was no combustion, but I am blowing, and I am actually shedding vortices here, and there is a resonator attached. So the vortex, so aerodynamic sound is produced by vortices when the vortex has a trajectory which is perpendicular to the acoustic streamlines. So here the Helmholtz resonator has this bulk oscillations which leads to a oscillation in the neck, the velocity oscillations in this neck region, which is this way, and the vortex causes this path. So then it makes sound, and so aerodynamically you can have sound, but there needs to be some resonator associated with it, and this coupling has to be strong, then you can get it. And that is one possibility is you see in whistling, or another thing is in flute, and so on. So in general there is this mechanism called lock-on. So we are talking about vortex acoustic or flow acoustics, okay, and there is flow acoustic, combustion. So all three can lock on, or you can have structure and acoustic lock on. So for example, you have cables in water and then flow around them, and the cables will vibrate because the vorticity, and so there is a lock on between the cable vibration and the vortex shedding, or the flags fluttering, and so on. So you have or this aeroelasticity where the vortex shedding locks with the structure. So you are having two different resonance phenomena coupled with each other, and then that leads to large amplitude. That is the general class of problems we are looking at, and it is a very big subject. I would not be able to do justice to the subject at all, but I will just briefly mention the points. So just to speak about this problem, so we look at large solid rocket motors. So large solid rocket motors, specifically write this. And I want to emphasize this word large, because large solid rocket motors are cast in segments. Small motors like the ones in small missiles, they can be cast in one shot, but if you have a very large rocket motor, let us say typically of the order of 20 meter or so, it is very difficult to cast in one shot, because by the time you pour the propellant, and it will take quite some time. You can imagine to fill up 20 meters or something with 3 meter diameter with propellant. That is something like, we are talking about 200 tons of something being poured, and it is going to take time, and by the time you are still the bottom would have said you are still pouring at the top. So this can lead to stresses and then the propellant can crack and so on, but they would want to make it as large as possible, which they can tolerate. So typically you can have segments which are 5 meter long, 7 meter, 8 meter long. I think in the future it is quite possible that you may have segmentless motors which are 20 meter long, but at the moment they do. So what they do is you cast this motor into segments. So if you have the grain this way and this is the propellant, this would be cast in segments. So they say this is one segment and this is another segment. Let's say we have put 3 segments. So if you remember, the PS1 has actually 5 segments. This is the motor which is used in GSLV and PSLV. The new motor ISR was building called S200. This has 3 segments. I think Ariane's MP5 motor has also got 3 segments, I think. So what they do is between the segments you have what is called the inhibitor. So this is some material which will burn slow or inhibits the burning. So otherwise what will happen is you can never fit something which is really perfect. There will be some gap, and then you will have the propellant start burning from the side, and then there will be a sudden increase in, as that start happening, there will be a sudden increase in flow rate, and then eventually the in a solid propellant, the propellant itself is insulating the outer casing structure, as we saw in last semester in propulsion class. So we want the propellant there, we do not want the gases to burn and come in contact with the wall. So we put this inhibitor, and then after some time this rocket will these inhibitors will protrude out. So this is, let us say, at the start, and then at some time later the inhibitor burns at a, almost does not burn out, burns at a much lower rate. So now it is almost like some discs or orifices inside a tube, and you have vortex shading. Okay. So this vortex that is shed will come back and come here, and right as it comes here the next one may be shed, and as it comes here and impinges here you send the acoustic wave back, and this gets into a feedback where as this is a, so normally it sheds in some frequency, but when you are under the lock-on circumstance the acoustic wave reinforces the shading, and then you get loud amplitudes. So you can have if there are 2, you can do this at home, you can put 2 washers in a pipe and blow air, you will get a nice tone. And another possibility is if you have this inhibitor is thick and there is flow, the front part will separate, but it will reattach and then again separate, and there is some kind of feedback there, and that will also produce sound. And yet another possibility is if you have a nozzle which has a bucket like structure, because of the gimbelling mechanism there will be some space provided here. So what will happen is this vortex, so this is where the gimbelling mechanism is, so this vortex will travel over this cavity, and then it is like my blowing over the bottle. So you have this this works like a Helmholtz resonator, and then you make the sound, and then it creates the sound here as the vortex goes over this. So there are many different ways in which this vortex sound can be produced, and even if you make a small fraction of the mean pressure, see these things have very high mean pressure like 60 bar and so on. So even if you have a very small fraction of the mean pressure as the fluctuating oscillation fluctuating pressure, you still have possibility to create enough structural damage. So in this case, even if you do not have any combustion, just the aerodynamic instability itself may be sufficient to cause some problem. So we have to check if, I think we can probably tolerate 0.1% of pressure oscillations or 1% of thrust oscillations. So if they are below that, then I mean the motor is okay, but anything more, I think motor would be unsafe. So here is another case where this coherent structure is creating problem, but it's more like a aerodynamic instability. So we are not having, the combustion is all happening just over the propellant surface. Now even if you don't have these inhibitors, if you have radial injection, like a, I mean propellant burning is like a radial injection. So if you have a situation where you have gases coming out this way, eventually there will be vortices being set up, because this flow is a inherently unstable flow, the radial injection flow. And even if you do not have vortices, and if you have a gimbal nozzle and there is a cavity there, there is a possibility of making sound. So I will give another example which is non-aerospace. We have gas lines. I think in other countries this is I mean natural gas is a very big source of energy. I think there is a lot of natural gas now in Andhra Pradesh. I think it has been discovered some years back, but we are not really have a good supply system set up, but eventually it will be. I think in Bangladesh has a lot of natural gas. So you have big lines this way, and then you have branches and so on, and these lines are very very long, and sometimes people, some branches may take more gas, some may not need gas, some may. So sometimes the moment you close some branches, many times actually instability develops, because you have a vortex shedding, and now you have like a resonator here, and then you have very large amplitude sound, and it will be quite strong, and the ducts are very long, so, and the vortices are strong, they can travel long, the sound wave will travel quite long, and as any sound wave will travels, will be discussed, it will steepen into a shock, so you can have large amplitude shock waves coming and destroying this, rupturing this pipelines and so on. So when you have natural gas being distributed this way, so anytime you close this branch, I mean if there is a flow, then I think this will not be a problem, because this vortex will be disrupted, but if not, I think you will have a resonator here and the vortex is crossing the lines of acoustic streamlines, and you have large amplitude oscillations, and then you can cause a lot of damage to the pipes.
Does this happen with water pipes also?
I am not aware of this. I have heard this problem mostly happens in gas, natural gas or airlines, but in water I do not know, to be honest.
Water has more viscous, so
there are some other mechanisms like water hammer or something, but
Hammering is because the pressure increases rapidly.
yeah, so I do not know about this kind of mechanism. I have not seen anyone report this. Any questions? Okay, so the next thing to look at is the possibilities of passively controlling these oscillations. So there are two possibilities. One is to we can disrupt the coupling between the heat release and the pressure oscillations. Oh no, I have to get to the other part, the lock on, sorry. So here actually the vortex is locking onto the acoustic field, okay, but you can have also, so there are three situations. I will just draw this graph and we can continue the discussion in the next class. Going back to the question that Sabirish asked, I will take 2 minutes more. If you have a class after this, yeah, it's okay to go. So we will plot dominant frequency versus Reynolds number and amplitude versus Reynolds number. And if so, typically the vortex sheeting frequency would go like this. It will be like you have a, we saw that there will be like a Strouhal number of 0.25 or 0.5 or something, and you have the vortex sheeting frequency go on. But the duct acoustic modes will be, they are constant. I mean there is the first mode, second mode, third mode, they are harmonic. So when you are in this region, so you will have initially the frequency coming up like this, and then you abruptly it locks to here, and then you come to jump to the next branch. Of course there will be some hysteresis, and then you go here, and eventually it cannot lock on anymore, so you continue to after some time it will continue to go this way. And every time the lock-in happens, if you look at the amplitude, you will see some pattern like this, and where it is locking to the first mode here, then it will jump to the second one, then it will jump to the third one. So this is what is happening in this situation where we drew here. Now the situation in a combustor will be different. I will talk about it next class because